Welcome back, boys and girls. We are going to pick it up from where we ended, and we are going to explain galvanic cells and electrochemical cells and just to see if we can answer a typical examination question. So this is what we are going to do. I'm going to start by giving you a detailed distinction between a voltaic or a galvanic cell. So in an exam, they will always specify what exactly are you dealing with. Is it a voltaic cell and an electrochemical cell? So when they distinguish those types of cells, how does, what implication does it have in terms of your approach and your applications you are going to do here? So I want you to follow me through my explanations here and make sure that you understand clearly what we are talking about and be able to make appropriate representations of these cells, be it diagrammatically and also the interpretations and calculations, because in some instances they will just give you a scenario or some information and then they ask you to draw or to represent a typical cell which you should be able to identify as either a galvanic or an electrochemical cell. So the first thing I want you to understand is that the words voltaic or galvanic are used interchangeably. They refer to the same thing. So don't get confused in an exam when you are so used to galvanic cells and boom, in an exam they are asking you about a voltaic cell. And then you get so lost and stuck, you can no longer relate what exactly are we talking about. Familiarize yourself with these terms as they play a very important part in distinguishing cells as they occur. So let's go into the details of voltaic or galvanic cells. We are saying that in voltaic or galvanic cells, a spontaneous reaction generates electrical energy. But in an electrolytic cell, energy is actually absorbed. So, and where is it absorbed from? It is absorbed from an electrical source to drive a non-spontaneous reaction. Am I making myself clear? I will repeat again and show this by means of an illustration. I'm saying in a voltaic or a galvanic cell, we generate electrical energy. Meaning that in the setup of a voltaic or a galvanic cell, we don't expect you to show a connection of a battery, because it's you who is going to generate the energy that is going to drive the the electrochemical process. And because energy is generated internally, the reaction is going to be spontaneous. But in an electrochemical cell, we are saying energy is actually absorbed from a source, and then it is driven through the system until it sustains a reaction, and for that reason the distribution of energy through the components of the cell makes the reaction non-spontaneous. So these are the main identifiers of what can be isolated as a galvanic or a voltaic or an electrochemical cell. This is what happens. We are saying in both the electrochemical and the galvanic cells, there are common components that are uniform or common. Like for example, the electrodes, we are saying in both cells, we need electrons. And those electrons, they conduct electricity between the cell and the surroundings. And then we have got an electrolyte, which is a mixture of ions involved in reaction or carrying charge. And there is a salt bridge, which completes the circuit and provide a charge balance. So in an exam, they may ask you to describe the role played by the following components of a typical cell. And then they identify all these things: an electrode, an electrolyte, and a salt bridge. Do we remember all these things from our grade 9? What purpose do they serve in the setting up of an electrochemical cell? So I'll repeat again. I say the electrodes, they conduct electricity. So if you compare the galvanic cell, we are saying it is at the electrodes where some electrons are picked up and other electrons are discharged into the solution. And when that happens, we will have a continuous flow of electrons while the solution or the salt bridge will complete the circuit. So in electrolyte, we are saying it is the source of ions involved in reaction or carrying the charge. So when the electrons are discharged at one end, they need to be carried or transported across the solution to another electrode. And what does that is the electrolyte. And the electrolyte contains ions which help to pick up the electrons, carry them across the solution, and discharge them at another electrode where they are picked up and circulated through the cell. And a salt bridge, like I'm saying, here we are talking of electricity and generation of energy, and we know that we do not have a flow of charge if a circuit is not complete. So the salt bridge helps us to complete the circuit. Okay, so what happens at the different electrodes in an electrochemical cell? So we are saying that there is an anode. Ladies and gentlemen, I've noticed over the years that there is this ambiguous uncertainty on what happens at the anode, or what is an anode, and what happens at the cathode, and what is a cathode. And others, they've reached a conclusion of saying that it depends on whatever interpretation you attach, anything goes at any of the electrodes. Is it true? I want to put this as a thumb's rule. Look, an anode performs, or the behavior of an anode is one and only one function, where we are saying at the anode, come hail, come thunder, oxidation occurs at the anode. And at the cathode, reduction occurs at the cathode. So we do have active electrodes, and we also have inactive electrodes. So an active electrode, they also participate in redox reaction. So you see that in a setup of an electrochemical cell, you can tell whether this electrode is active or not active. In some instances, the electrode itself, it will disappear or dissolve into the solution. While in others, a lot of things happens. They build up in terms of the size of the electrode during the chemical reaction. While in the inactive electrodes, there are only sites at which oxidation and reduction take place. So this will happen between the electrons and the ions which are in solution already. Okay. So let's go into the fine details of a voltaic or galvanic cell. We are saying this is a device in which chemical energy is changed to electrical energy. So this reaction, this cell witnesses spontaneous reactions taking place in the system. Okay. So here is a typical representation of a galvanic or voltaic cell. So here we are. We have got an electrode here and another electrode, which I am saying, boys and girls, this is an anode. Remember, we agreed earlier on that what happens at the anode, oxidation occurs. What is oxidation? Remember, oxidation, we said oxidation is loss of electrons. So let's try and relate here. Who and where and why are electrons are being lost at the anode. So hear me very well. We agreed that there is a solution, and in this solution we called an electrolyte, and in the electrolyte there are ions, and these ions, they serve a purpose of transporting electrons through the solution. So what is happening here is that it is the ions that have picked up electrons and carry them through, and then when they reach the anode, it is the those ions which now give up that electron, and that electron is picked up by the anode. So what is oxidation? We are saying oxidation is loss of electrons. And what is losing electrons here? It is the ions in the solution that had picked up electrons somewhere else, carry them through the solution. When they get to the anode, they are forced to give up their electrons. So what I don't want you to confuse this phenomenon is others, they will think that it is the electrode itself which is giving out electrons, and then the ions are picking up the electrons from the anode. No, it is the ions which are losing their electrons, and their electrons are picked up by the anode, and the anode carries the electrons out of the solution, and then they are carried through to the cathode. And then at the cathode, what do we expect? We are saying at the cathode, the electrons are forced into the solution, and then when they go into the solution, we do have ions there which are available to pick up the electrons, carry them through the solution, and the process goes on and on. That's why you see that the direction of flow of electrons in a galvanic cell always is from the anode to the cathode. Look why I'm representing it. I'm not saying from the cathode to the anode. We are saying it is from the cathode to the, it's from the anode to the cathode, not from the cathode to the anode, because here the electrons are not going directly from the cathode to the anode. They are going into the solution, and it is the ions in solution that will pick up the electrons and carry them to the anode. So we are talking of a direct interaction here. We are saying electrons move from the anode to the cathode. So look at the arrows which are showing the movement of electrons through the voltaic or galvanic cell. So, ladies and gentlemen, let's familiarize ourselves with this, okay? So here is a practical representation of this phenomenon which we are going to perform an experiment in our next presentation. We are going to do this experiment where we have got a spontaneous reaction between zinc and copper. What we have in here is a copper sulfate solution, and these are zinc electrodes. So what is actually happening is that zinc is picking up electrons, and yes, the zinc is actually giving electrons, losing electrons into the solution, and those electrons are picked up by copper, and copper becomes solid particles. And while at this stage, this is what is happening, the zinc plus the copper is actually picking up electrons, and then it becomes a solid, while in the other while the zinc goes into the solution. Okay, so this is a typical representation of a spontaneous reaction between zinc and copper. We are going to do that experiment so that you have a feel of what is actually happening here. Okay, so there we are. So like I said in an exam, they might give you a question in which you are supposed to draw a voltaic or a galvanic cell, meaning that they will just give you a set of information, and it's you who has to draw the electrochemical cell and attach all the information and the interpretations you're supposed to do this. So here we are. We are saying this is one a part of the cell, and here we are saying this is a zinc plate which is acting as an anode, and we agreed that at the anode there is oxidation where the ions in the solution are coming here and give up their electrons, and the electrons are transported through the anode out of the cell through a conductor to the cathode. And how do we know that the electrons are moving? We can put a voltmeter to measure the potential difference. And then when the electrons come into the copper electrode, the copper electrode will discharge the electrons into the solution, and then the copper ions will will become 2+ like this, and then the ions move through a salt bridge of sodium sulfate, and then we'll have a balance of charge between the components of the cell. So if we are to represent this by means of half reactions, we are saying this is what is happening here: oxidation half reaction. The oxidation half reaction, we are saying zinc, a solid, is going into solution, and it turns into zinc 2+, and we have got 2 electrons forming over there. Okay, and then the 2 electrons, you can see how they are going up out there to the cathode. So this is the half reaction at the anode, oxidation as we know it. Okay, and then the reduction half reaction here at the cathode, you can actually see that the copper 2+ are picking up the 2 electrons which are coming from the zinc. And then when it does that, it forms copper solid particles. And the overall reaction where we are combining the two, you will see that we are saying the zinc solid is reacting with the copper 2+ ions, and we have got exchange of electrons, and then the zinc become zinc 2+, while the copper 2+ become a copper solid. So if you are to look at what is practically happening to the electrodes themselves, remember we agreed that the zinc is moving from the electrode, dissolving into the solution. Do you see the zinc depleting or becoming smaller and smaller as the individual atoms dissolve and go into the solution? And look at the copper. This is the original copper. Look how it looks like. It now have got some deposits of copper atoms surrounding or forming around the electrode itself, because the copper ions in the solution, they are depositing onto the copper cathode, and then they pick up the electrons, and the solid copper atoms form like that. I hope this is quite clear and straightforward for you to understand what's happening. So you realize that this salt bridge, it serves the purpose of allowing ions to go in there to balance up the ionic charge over there and that side, and then for that reason it serves as a connecting parameter which completes the circuit. Okay. So for this voltaic cell, we can show, what we have just shown here, this is a reaction, a cell in which the electrodes themselves were involved or participating in the reaction. So in other words, we are saying this is an example of an active cell in which the electrodes are part and parcel of the reaction. Okay. But in this case, we are saying this is a representation of an inactive cell, electrodes, where the electrodes themselves, they neither dissolve or grow during the reaction. So take, for example, where we are using carbon rods So these carbon rods, we know that carbon is extremely stable. It does not react under ordinary conditions. So we don't expect the carbon to dissolve or to deposit. So look at this. We are saying in this solution, we've got iodine or iodide ions, while in the other one, we've got permanganate ions in an acidic environment. So what actually happens, we are saying this is still our anode. And what is happening at the anode? Oxidation. So how is the oxidation taking place? We are saying oxidation is loss of electrons. So meaning that in this case, the electrons, the iodine ions here, they are I minus, meaning that they are carrying a negative charge, so they lose their electrons, those foreign electrons they are carrying, so they give them up to the carbon electrode. So an oxidation half reaction taking place at the anode of an inactive cell. We are saying two iodine ions in solution, they actually pick up they lose the electrons and then become solid particles, and then the electrons go through the anode to the cathode. And then for that reason, this becomes the oxidation half reaction. So what happens at the reduction half reaction? We remember when we made some representations earlier on when we were balancing equations, we had this kind of a situation where we've got the manganate 7 plus and we have got the H plus ions. So electrons had to be moved around here, and we agree that the manganate will have to react with the 8H plus so that we remove these oxygens to form water, and then we must have 5 electrons coming in and they will be picked up by the manganese to form manganese 2 plus. So the manganese is undergoing reduction from 7 plus to 2 plus by picking up 5 electrons. So those 5 electrons will have to come from the iodide ions giving up their electrons to the carbon electrode of the anode. So if you put everything together, you see that one iodide atom will have to give up 1 electron. Okay, so if one iodide ion gives up 1 electron, we know that when iodine atomizes, it forms a diatomic molecule. So meaning that we will always have 2 electrons generated per pair of iodide ions, like represented in the oxidation reaction and that. So what does that imply? It implies that for us to account for these 5 electrons, we have to multiply everything by 2 to make them 10. So this is what happens in the overall cell reaction. We have 2 manganate ions and 16 H plus ions, and we need to have 10 iodide ions to form 2 manganate 2 plus and 5 iodine molecules and water, like that. So boys and girls, this should not give you problems to account for it, as we emphasize on dealing with half reactions. And I was telling you that it is important for you to understand how to handle half reactions, so that when you bring it to these electrochemical cells, you are able to account what is happening at each electrode, because each electrode represents a half of the cell, and what is happening there can be accounted for in both chemical and mathematical terms. As you are going to see, we are going to measure the overall redox reactions taking place there, and then we are going to perform calculations to find the overall cell potentials. Okay, so here we are. We are saying that in the phenomenon which was represented earlier on, zinc is giving up, is picking up electrons from copper, and copper becomes ions in solution, while zinc becomes a solid. So zinc gives up electrons to copper. So zinc is capable to push so hard on the electron gradient and will generate a greater potential energy and greater electrical potential. So these potential spontaneous reactions, they occur due to relative difference in metals' ability to push or to give away electrons, and when they strongly push electrons out of their system, we are saying they facilitate an ability of electron flow through the electrochemical cell. Okay. So that brings us to what I just highlighted earlier on when I say that your understanding of the half reactions will enable you to explain and account what is happening at each and every electrode in the electrochemical cell, and from there you are able to make both chemical and mathematical representations there. So for us to determine cell potential, we need to know what is happening, how it is happening, and when does that happen. So meaning that you can be given a wide range of materials and you are asked to pick up materials and use them to make an electrochemical cell. How do you determine what do I pick up and use as an anode? What do I pick up and use as a cathode? Because at the end of the day, your choice of the materials you are going to use is going to determine the behavior of those materials and what kind of an electrochemical cell you are going to make and whether it's going to generate electricity. Because remember, we talked about a galvanic cell as a device that actually generates energy or generates an electrical flow from which we will be able to make use of the energy that is generated from this. So we are talking of cell potential and electromotive force. What are we talking about? This is more one and the same thing, and the phrases are used interchangeably. So we are saying a cell potential or an electromotive force, it is the pull or the driving force of electrons measured as potential difference and a voltage. Okay. So in other words, we are saying E cell is equal to the work or electrical potential energy over the unit of charge moved. And the unit of charge here we are talking about amount of electrons which are moved through the system. And we know that there is a constant that we use to refer to the amount of charge in an electron. Okay, we're going to go into those details very soon. So in other words, we are saying E cell is equal to joules over charge, which is equal to voltage. I expect you to claim this if possible, so that you can make use of this in future. Okay, so here we are saying we have got this representation of a galvanic or a voltaic cell, and this is zinc, this is copper, and this is a copper sulfate solution and a zinc sulfate solution, a concentration of 1 molar, and when this was allowed to undergo a simple reduction, and remember we are saying this is a spontaneous process, the voltage measured here was found to be 1.10 volts. So what does this imply, boys and girls? We are saying we can determine the E cell by simply saying you measure the cell potential under standard conditions. So elements in the standard states, that's 298 kelvins at 1 atmosphere. We've got all solutions in 1 molar and all the gases at 1 atmosphere. So what happens then? Given this standard voltaic cell, where we are using a hydrogen electrode here, we can measure the cell potential of the zinc, which we don't know what it is, and we can compare it to the standard hydrogen cell, which we are saying under standard conditions, this is measured to be 0. So the oxidation half reaction at zinc, remember we agreed that this is an anode. So what happens there? Zinc goes into solution and form zinc 2 plus ions and gives away 2 electrons, and the 2 electrons are carried out down to the standard hydrogen potential, the standard hydrogen electrode, where the hydrogen is a gas at 1 atmosphere and the platinum wire is used to carry the charge like that. So the reduction half reaction, it is the hydrogen which is losing, which is H plus, and is picking up the electrons to give out hydrogen gas. So that's why you are seeing these bubbles of hydrogen being given off. So the overall cell reaction is such that hydrogen, zinc, a solid, is reacting in a redox reaction with H plus to give us zinc 2 plus hydrogen gas. Okay, so how do you determine the cell potential here? We are saying under standard reduction potentials, E naught values for reduction, half reactions with solutes at 1 molar and gases at 1 atmosphere. So this is what is happening with our copper. The copper 2 plus picks up the 2 electrons and becomes copper atoms. And the standard reduction potential is positive 0.34 volts versus the standard hydrogen electrode, just like the one which we showed earlier on. While the sulfate will react with 4H plus and 2 electrons to give us sulfurous acid, and the water molecule with the standard electrode potential is 0.2 versus the standard hydrogen electrode. Okay, so for that reason, it takes us to this table. Ladies and gentlemen, these are constant values of measurements that were done under standard conditions, and all these species were measured against the standard hydrogen potential. And what is this standard hydrogen potential? We are saying that it was measured to be 0. So everything which you are going to get there is as a result of the electronic interaction of these species. So as you can see, fluorine has got the highest standard electrode potential, E naught, which is plus 2.87, and as you go down, it's decreasing consistently down to silver, which has got a standard potential of plus 0.22. So what can we say about these ones? Because we are, or what we have observed already is that all these values are positive. What does that mean? Let me take you back a little bit. So if I take you back, you can actually see that whenever you get a positive value of the voltage, it means that this material which is positive, it works very well as an anode where oxidation takes place. So it allows, or it means that the higher the positive value, the faster or the more the material behaves like this, where it quickly goes into solution and gives up the electrons. So that's why it is best to use that material as an anode. So if you look at this one, you actually see now the values are changing from positive to negative. So what does that mean? What does that imply, boys and girls? So you can actually see that these species which are more negative, they are best used as the cathode. Okay. So here are some of the voltaic cells and their respective voltages. So here, when you've got a voltaic cell and the voltage, a common alkaline battery, I think you've all bought some batteries, and if you look at them, they've got 1.5 volts, The lead acid car battery has got a voltage of 2, but the 6 cells has got 12 volts like the ones which are used in your cars. Your calculator battery is 1.3, the electric eel is 0.15, and the nerve of a giant squid 0.07. Okay. So what are we saying? We are saying that these electrochemical reactions are very important in terms of accounting for the practical things which we experience every day, and we can also manipulate these half reactions and the cell potentials to decide what's going to happen, where, when, and how. And you can deliberately select materials, put them together in an electrochemical cell to achieve whatever reactions you want to do. So like in this case, we are using a reaction of calcium in water. And what is the product of this whole thing? We are producing hydrogen. So we can use this electrochemical cell for hydrogen production. Okay. So here is one of the systems which is used in the dental treatment of your teeth in what they call a dental voltaic cell. What's happening there? You've got aluminium or an amalgam. So they bring in aluminium foil, and this is what happens at the aluminium silver tin mercury interface. The aluminium will pick up electrons which are generated from this, and then you've got a silver lining here which will allow the reaction to take place such that you have a filling into your tooth as a result of the saliva that is acting as an electrolyte. Okay. So here is an example. Whenever you have got E cell which is greater than 0, you should know that it's a spontaneous reaction, a galvanic process. And where E cell is less than 0, the reaction is not spontaneous. And when E cell is exactly equal to 0, you should know that the reaction is at equilibrium. Okay. So to conclude this reaction, this session, we are going to have a few calculations in which you show how to determine the E cell or the cell potential. So here we are saying that under standard conditions, the standard E cell is equal to cathode minus anode all the time. This is what when you are carrying out electrons, calculations, we are saying when you have determined which of your materials is going to be your cathode and which one is going to be your anode, for you to determine the E cell is found by saying cathode minus anode. And how do you know that? We say you will know that by coming here. You choose your materials wisely, where you need to find out if your species is in the negative, is it going to be your cathode or your anode? If your species is in the positive, is it going to be an anode or a cathode? So how do you determine that? We are saying that in this calculation, we want to find out something which is spontaneous, meaning that when you do your E cell, where you say cathode minus anode, if your value is greater than 0, then you know that it is spontaneous. When it is less than 0, then you know that the cell does not work. It will not work. So you should make sure that your values you are going to choose. So like, let's say, for example, if I quickly show you here, let's pick up any one of the values here. So like, let's say, for example, you choose your zinc here, which is plus 0.96 plus 0.96 to be your cathode. Oh, sorry, remember earlier on we used it as an anode. So it's going to be your anode. And then you use, what else do you use? You use lead as your cathode. And lead here, it's minus 0.13. So it's minus 0.13. So if you use lead as your cathode. So we are saying that the standard E cell is going to be equal to cathode minus anode. So we are saying our cathode here is minus 0.13. So if this is minus 0.13 minus plus 0.96, what do you get? If you subtract this, so it will give you what? It will give you a minus 1 point, what? It's going to be 1 point, this is 9, 1.09. So if it is, you see it is giving us a negative value. So what does that imply if it is giving us a negative value? We are saying if E cell is less than 0, it means that this cell is not going to work. But if E cell is greater than 0, it will give us an spontaneous. But if E cell is equal to 0, it means that it's going to be in equilibrium. So what it simply means is that you need to just swap this. This becomes your cathode, and this becomes your anode. And if you say cathode minus anode, it becomes 0.96 minus 0.13. So if you add this, so this becomes a plus. When you add this, it will give you plus 1.09. So you see that a plus 1.09 is greater than 0. So for that reason, it becomes a spontaneous reaction. So boys and girls, these are the deductions you are supposed to make when you are deciding which materials to pick up as an anode or a cathode, because when your E values are more positive, it means the material is a strong oxidizing agent and more readily accepts electrons. If it is more negative, it means they are reducing agents and they readily give away electrons. So this is a summary of how we make use of galvanic electrons. So when we meet next time, we are going to talk about electrochemical cells, and then we answer a typical examination question. Thank you very much and enjoy. Okay.